Good morning to all. Today we are discussing about memory, registers, and aspects of system timings. Introduction. Many digital systems use memories for storing information. Memory in general purpose computers takes several forms, including semiconductor memory chips and magnetic disks and optical disks. Okay, it means that in many digital systems we are using the memories for storing information. For example, the general purpose computers, the memory existing in many forms such as semiconductor memory chips and magnetic disks and optical disks. Okay. And the second point in this chapter, we describe the various types of semiconductor memories. Since other forms of memories are much less frequently used in application-specific digital systems. It means that in this chapter we are studying about semiconductor memories because compared to all other memories, most of the time we are using the semiconductor memories. Okay, and now we are discussing about classification of the memories. Okay, that is first the basic operation mode. Based on the operation mode, the memories can be classified into two types. That is first one is the read-write memory and second one is the read-only memory. In this read-write memory exists two operations such as read operation and write operation. Okay, and the examples of the read-write memory is static RAM and dynamic RAM and EEPROM and EEPROM and flash memory. Okay, and the read-only memory examples are mask programmable read-only memory. Okay, and second one is data storage. Based on the data storage, memories can be classified into two types. That is volatile memory and non-volatile memory. Okay, volatile memory means, for example, this is the memory. Okay, and here we are concerned the address locations of the memory. Okay, this is 00 memory address and this is the 01 location. This is the 10 location. For example, with respect to the writing signal, we are store the data in this location. Okay, we want to store the information in the memory location. We require the power. Okay, for example, the power supply is interrupted. The stored data is lost. That is your concern on volatile memory. Okay, for example, the power is interrupted also. Okay, we are not lost the data. That is your concern on non-volatile memory. Okay, the examples of the volatile memory are static RAM and dynamic RAM. Okay, and again this non-volatile memory can be classified into two types. One is the read-write memory. The examples of the read-write memories are SRAM, DRAM, EEPROM and EEPROM and flash memory. Okay, and second one is the read-only memory. The examples of the read-only memory are mask programmable read-only memory. Okay, and based on the access method, the memories can be classified into two types. Okay, one is the randomly access the memory. That is we are concerned the random memory. Okay, the examples of the random memory are read-only memory and static RAM and DRAM and EEPROM. And the second one is the non-random. Okay, the examples of the non-random memories are the serial access memory and the second one is the content access memory. Okay, and finally in this chapter we are studying about two types of the memories. Okay, that is the static random access memory and the second one is the dynamic random access memory. Okay, and now we are discussing about comparison of dynamic RAM and static RAM. Okay, and coming to the dynamic RAM, each memory cell stores one bit of information. It means that it is a dynamic RAM store the one bit of information. So here we are using the each memory cell can store only one bit of information. Okay, coming to the static RAM, in SRAM a form flip flop hold each bit of memory. Okay, And coming to the dynamic RAM, it has the transistors and capacitors. And in the static RAM, a flip-flop takes 4 transistors. It means that in this dynamic RAM construction we are using the transistors and capacitors, but in the static RAM we are using the 4 transistors. Okay, and third point, dynamic RAM has to be refreshed dynamically thousands of times per second. And here the static RAM no need to be refreshed for the storing the data. Okay, and next one, slow down the memory. The dynamic RAM is the slow down the memory, but the static RAM is the faster than the dynamic RAM. For the stored information, the dynamic RAM requires less area, but the static RAM requires more area. Okay, and the dynamic RAM is less expensive, and the static RAM is more expensive. Okay, and the dynamic RAM is used in main memory, and the static RAM is used in cache memory. Okay, and the dynamic RAM is on-chip memory, and the static RAM is off-chip memory. Okay, and the dynamic RAM have the charge leakage problem, and the static RAM does not have the charge leakage problem. Okay, and compared to the dynamic RAM, the static RAM requires low power consumption. Okay, and dynamic RAM is volatile memory, and the static RAM is non-volatile memory. Okay. Next, we are usually discussing about dynamic RAM and static RAM. Okay. Before going to explaining about dynamic RAM and static RAM, few minutes we are discussing about system timing considerations. The system timing considerations are very important for working of the memory system. Okay, so the system timing considerations are, first one is a two-phase non-overlapping clock signal is assumed to be available, and this clock alone will be used throughout the system. It means that, for example, here we are considering one of the memory system. Okay, that system should perform the writing operation for store the data at a particular memory address locations, and read operation for read the data from that particular memory address location, and sometimes we are refresh the data in the particular memory address locations. Okay, so we want to perform all these operations. Definitely, that memory system is required the two clock signals. Okay, and these two clock signals are non-overlapping clock signals. Okay, for example, here we are considering this is the one clock signal and this is the another clock signal, and these two clock signals are non-overlapping. It means that the same instant of time, the same state is not existing in these two signals. For example, this instant the clock 5 is logic 1 and the clock 5 is logic 0. And the next instant of time, the clock signal 5 is logic 0 and the clock signal 5 is logic 1. Okay, so these two clock signals are non-overlapping. And the second point, clock phases are to be identified as phi 1 and phi 2. So we are indicate these two clock signals. One is the phi 1 signal and one is the phi 2 signal. Okay, and the third point, bits are data to be stored or written to storage elements and subsystems on phi 1 of the clock. Write signals are ended with phi 1. It means that, for example, here we are considering the one of the memory system. This system have different memory address locations. Okay, for example, here the memory address locations are 00, 01, 10. Okay, based on the writing signal, the data is stored in that particular memory address location is 01. Okay, now this writing signal are synchronized with this phi 1 signal. Okay, and next point, bits are data written into storage elements may be assumed to have settled before the immediately following phi 2 signal, and phi 2 signals may be used to refresh storage data where appropriate. It means that in the particular memory address location we are store the data. Okay, after storing the data, immediately we are refreshing this data. So after refresh also, the data is stored at the same address locations. Okay, so we want to refresh this data in this memory system. We are using the 5 to clock signal. Okay, and next point, in general delays through the data paths, combinational logic are assumed to be less than interval between the leading edge of the phi1 of the clock and leading edge of the following phi2 signal. It means that, for example, here this is the leading edge of the clock signal phi1 and this is the leading edge of the clock signal phi2. Okay, the difference between or the delay between these two clock signals is very less because its duration only the memory address location data is refreshable. Okay, and next point, bits or data may be read from storage elements on the next to the phi 1 of the clock. That is, read signals are ended with phi 1. Obviously, RD and W are generally mutually exclusive to any one of the storage element. It means that with the help of the reading signal, the data is read from that particular memory address locations. Okay, so this read signal also synchronizes with the same clock signal phi 1. Okay, for example, in this figure, this is the clock signal phi 1. Okay, with the help of this writing signal, the data is stored in that particular memory address location. After storing this data, we are reading from that same memory address location. Therefore, we are using the read signal. And here, this writing signal and read signal are mutually exclusive events. It means that at the same time, these two signals are not performing the operation. Okay. And next point, a general requirement for the system stability is that there must be at least one clock storage element in series with every closed loop signal path. It means that, for example, here we are considered the D latch. Okay, so here we are using the two inverters, and here with the help of this N MOSFET, we are get the one closed loop signal path. Okay, and here the earlier stage output is, for example, logic 0, and we apply the clock signal equal to 1. So when we apply the clock signal equal to 1, this MOSFET is acting as closed switch. Therefore, this 0 is getting the input side. Okay, and for example, we apply the input is, for example, 1. Okay, and here we get output also 1 during the clock signal equal to 1. For example, at the same time, we are giving the clock signal equal to 0 to the base terminal of this N MOSFET. At the time, this N MOSFET is acting as an open switch. At the time, the output of this D latch is earlier data is repeatable. It means that in the earlier stage, the output is 1. Okay, so this 1 is repeatable up to apply this clock signal equal to. So with the help of this, we are concluding that this is the at least one clock storage element in series with every closed loop signal path. Okay, so these are the system timing considerations. With the help of all these timing considerations, we are designing the memory system. Okay, thank you.